Good day, class. My name is Jamie Jacobson. I'm going to be doing a presentation on bioprinting to go along with the step 2 of our final project. The background to the scenario was that your father needs a kidney and you heard about bioprinting. What's the ability of him to be able to get a bioprinted kidney since he's been on the organ donor waiting list for quite some time? So we're going to get into that, and I'm going to start off by explaining a little bit what bioprinting is, talk a little bit about related technology, and then we're going to talk about the feasibility of actually accomplishing that. Will Dad get his kidney? So what is bioprinting? Bioprinting is a process that's really similar to 3D printing, and I think that's a little bit ubiquitous at this point. Everyone's seen 3D printing. You can even buy in regular shops, not just like an Etsy shop, something that's been 3D printed. But it's a little bit different in the fact that with a 3D printer, a more normal 3D printer, the polymers that are used are things like plastics, whereas a bioprinter uses what's known as bio ink, and there's still a polymer in there, but they're called biopolymers. So the type of polymers mean that printing techniques have to be a little bit different because you're not printing, I don't know, a cool-looking dragon egg. You're printing either tissue or entire organs. Now, the current place that we're at with bioprinting is actually kind of advanced. It's a very cumulative kind of technology, and we've been doing research in a lot of the related technologies like stem cell usage and making lab-grown tissues. So we're in a kind of refinement rather than broad research part of that life cycle. And the significance of bioprinting is very interesting because we have this idea of an end goal, which is, hey, I'm going to bioprint an entire heart. But at the same time, we're not quite there yet, and it has other use cases, which we'll talk about in the next slides. So, what does organ transplants look like currently? Organ transplants are from the top down controlled by the Department of Health and Human Services, HHS. Below the HHS is an organization known as the OPTN, or Organ Procurement and Transportation Network, which manages the Health Resources and Service Administration, HRSA. And all of that is to say that they are the ones that set up programs for organ donation and who gets the organs, who gets onto the waiting list, why and how that's all managed. That is then further subdivided, and responsibilities are given to other entities such as individual states that will have their own organ donation list, hospitals and hospital networks, since they're the ones that are actually putting the organs in bodies, and also to independent contractors, because the government doesn't typically do a lot of its own work, it contracts it out. So that's the regulatory kind of control arm of it. But it is a voluntary basis, so not everyone's made to be an organ donor, obviously. Because not everyone's an organ donor and you have to wait for someone most often to die before their organs are harvested, that means that there's a lot of limited supply. And even when there is an organ available, the recipient of the donation has to be compatible to the organ. And even when that happens, the recipient will then end up being on things like immunoblockers for really the rest of their life. And even when that works, there's often a life expectancy for that organ. So even if I were to get a heart transplant today, there's a large chance that in anywhere from 10 to 15 years, I'm going to need another transplanted heart. It doesn't necessarily stay with me for the rest of my life. So with all of these issues, rejection, the need for immunosuppressants, etc. These are some of the things that we're looking for to try to solve with the bioprinted organs. With that said, let's look at the technology of it. What does a bioprinter look like as compared to a 3D printer? So a lot of the parts are actually very similar, right? It's kind of the same concept in which there is going to be a headpiece or an extruder, right? And it is going to push a filament, in the bioprinter's case, that is bio ink. And it's going to push it onto a receiving platform, which is the bed. And it's going to work in 3 dimensions, so an X, Y, and Z axis. And depending on who is producing this bioprinter, the parts move in different ways, and sometimes it is the bed, the print bed, that moves, and sometimes it is the head that moves, and sometimes it's both. And then the other major difference between a bioprinter and a conventional 3D printer is the bioink itself, right? So the bioink is a cluster of cells that's been mixed in with a gel. Most conventionally, that's what's referred to as a hydrogel, and it is made up of a biopolymer. So in the same way that filament on a 3D printer is a polymer like PVC, they also have polymers that are suspending cells for bioprinting. It's just that the polymer used in the bioink, the hydrogel, is a biologically reactive or acceptable polymer. So something like gelatin, for example. Your body can actually take that in and it won't be too upset about that. I'm going to talk a little bit ahead of myself here and say that there are issues with the development and getting bioprinting to the place that we want it, right? And that's that in order to do it right, it has to be done at a very small scale. So there is a subclass of hydrogel known as microgels, right? And that is where the polymer itself is, it has an even kind of smaller molecular structure than what we've been using with previous iterations of the hydrogels. And when we're going smaller with that, we also want to go smaller with the extruder tips. And this all gives us better control and better ability to print the kind of structures and organs and tissues that we want to print. When we do that, again, unlike a conventional 3D printer, which can print freestanding structures, most often at least, the bioprinter actually prints directly into what's known as an extracellular matrix gel. And that's a type of nutrient-rich gel that gives structure outside of the printed structure. And it also is something that helps to keep this living structure alive throughout the printing process. And because it is a larger mass, only small masses can actually be kept alive in just that nutrient suspension. So that brings us to our first big issue, which is in order to keep these structures alive, we have to establish what's essentially blood flow and then what becomes actual blood flow into a body. And that's vascularization. Let's walk it back to the technology aspect first, though. Bioprinting is a cumulative technology that's come from researching other concepts, such as stem cell research, culturing and growing tissues in a lab, and the ability to grow artificially created biological structures. So all of those things have led us into the modern concept of bioprinting. So there's another kind of medical technology that's very similar, and it is using structures and then recellularizing the structure with different kinds of tissues. So you may have heard of the meat berry. This is a kind of common pop culture reference to, a bigger scientific concept, right? So there's this idea that you can decellularize an organic structure, and that's essentially taking some sort of detergent and destroying the cells in the item. It's very easily done with plants, so you can decellularize an apple and get rid of the cells and then leave behind just the structure of the apple, and then recellularize it in theory and now in practice with human cells, and you can use that natural plant structure with the cellulose and make, a bioprosthetic ear, for example. And I do have a picture down below of a 3D printed example of that, where a transplant ear was 3D printed using collagen, which again is still an organic kind of polymer that was 3D printed in and of itself. And there's this entire idea that we have been working off of for longer than we've been doing bioprinting, which is give a lattice or an underlying structure and let the body kind of grow over it. So bioprinting is taking that idea and taking it one step forward. Instead of carving an apple into an ear shape and then decellularizing it and recellularizing it in order to create this ear, instead we're just going to print the ear from scratch and give it the shape and the structure that way. One of the benefits of that is that now the body doesn't have to work around the underlying structure. It doesn't have to worry about working through and removing eventually the cellulose that was a part of the apple lattice. It's just, this is an ear, it is recognizable human tissue, it came from donor cells from the actual patient, and it just accepts it. But the use cases really don't stop there. What are the other benefits of bioprinting? So we've already talked on the first couple of slides about the really big things, right? Printing entire organs and doing transplants and essentially the logical extreme of it, right? But from the reading that I've been doing, it shows that a lot of the other use cases, and possibly even a more important use case for this technology, isn't whole organs. It's actually smaller structures, right? So broadly, all of this is what's known as tissue engineering, but more specifically, tissue engineering can be used with bioprinting to make smaller amounts of tissues that are not whole organs, right? So skin grafts, cartilage, connective tissues. Normally, whenever you have something like an ACL tear or the need to have a skin graft, you go to another part of the body and you kind of cannibalize that part for the surgery, right? The idea with using bioprinting for those kinds of tissues is that you get a new part rather than reusing a part from your body. So there's no sacrifice or trade-off to happen there. Organ transplantation, we've talked a bit about, right? And that's the whole functional organ that's going to be made from donor cells, grown, printed, stabilized, and then transplanted back into the body, right? But for research, it actually holds a very important niche, right? The example that's given is drug testing, right? The development of new medications. Part of the development life cycle for new medications is that it has to be tested not in a vacuum, but against actual, in a biological environment. So historically, we've done that with things like starting with mice or fruit flies, something that's similar to humans, and eventually we will go into human drug testing, right? Well, what if we could skip some of that, right? Not wholesale, but by the time that you get to human drug testing, you're invested, right? And it would be really bad and really costly for, I don't know, your antidepressant to show results and be effective on, say, mice in your experimentation, and then you get to human drug testing and all of a sudden it doesn't work. Well, what if you had a chunk of neurological tissue, a chunk of 3D printed brain essentially, and you were testing the drug directly on that before you get to the rats, before you get to the human drug testing? That saves a lot of time, and it means that you're getting the right refined product to your clinical trials rather than having to go back and forth to the most expensive parts. So it's very time and cost cutting there. But also disease modeling. Certain diseases that affect specific tissues, and I'll use the brain example again. There was, during the COVID pandemic, a noted symptom of brain fog, and another kind of novel symptom that was loss of taste, either permanent or temporary. So 3D printed neurological tissue was used actually to study those effects in a way that was, in the lab environment, more controlled, so that we could better understand why COVID was having those kinds of effects on people. So that's what it means by the disease modeling. And this all sounds great, and the technology's pretty much there. So why aren't we doing it? What's holding it back? There's a couple of known issues, and again, we're in like technological refinement, not necessarily technological broad research stage, right? And a big issue is scale. The smaller we can print with and the smaller the material is, the better it is, because we're talking about building, large cellular-based structures, right? That starts out tiny. There's a, I believe, Neil deGrasse Tyson quote of, if scientists or engineers were going to design the weirdest thing in the world, in the universe, that they couldn't, what would you ask them to design? And the answer is wood, because it's a super useful thing, and if we tried to make it, we'd fall right on our face, but nature made it for us. And it's kind of the same sort of thing, right? Organs, tissues, cellular structures, it's a very natural thing, it's a very robust thing, but it's very hard for us to engineer it back, right? So in order to do that, we have to work at just microscopic scales. So one of the big issues that I read about was that they just can't get extruders that are small enough. And there was a very elegant solution that we've kind of recently come to with that, and that's actually that instead of trying to make a needle in a small enough gauge, and which is amazingly costly, they're using the proboscis of mosquitoes. They are taking dead mosquitoes and they are very microscopically kind of dissecting it and then cutting out the proboscis and lining that proboscis with a UV curable resin and making a nozzle out of the mosquito proboscis. That is the scale that we're talking about. We need to go small. And I believe it was somewhere around like 300 times smaller than some of the previously used extruding heads, the nozzles. And whereas you were paying hundreds, thousands, tens of thousands of dollars for the single nozzle that could easily bend, break, what have you, the mosquito nozzle costs like 80 cents. So, a very novel and unique solution, but one that works. So the other thing about it is the difficulty of printing the large organs themselves, right? And any large structure that does not just survive in the nutrient-rich gels, which the structures that survive in the nutrient-rich gels are at their largest only like millimeters inside or 1 millimeter in size, right? Entirely too small. because you're working with the concept of, in order for the nutrients to get in, it has to diffuse directly over cellular membranes. And the way that larger samples, tissues, or organoids live is through vascularization, where there's actually, vessels to receive nutrients or blood supply. And that's been very hard to do because, again, nature just does blood vessels way better than we can. And part of the way that we've solved this with bioprinting is that we have multiple heads, right? So, well, you have one head that's printing the structure of an organoid or a larger structure, then you've got a separate head that is handling the vascularization. And that's, one of the things that's been pushing us more forward. But also, even if we do this, there's kind of nothing exists in a vacuum, right? And science exists for, the good of the people, as it was. So COVID kind of slowed up and in some ways accelerated the research into bioprinting. Resources were taken away from some of the R&D of it and some of the big projects, but it was also used, like I was talking about earlier, to study the virus. So again, part of the best use case is the research case, and so the use of bioprinting for modeling really got a boon in those couple of years, but some of the larger kind of ideas of it got put on hold. But who is it that's actually making the decisions with how this research is going? And the answer is the government, or at least, in part the government. So there is a large organizing body known as the United States Department of Health and Human Services, right? And that's just the American equivalent. There's also international bodies, right? But underneath the HHS is the OHRP, the Office of Human Research and Protections, and they are a mirroring organization for the FDA, right? The FDA handles food and drugs, and the OHRP handles the fleshy bits, right? So they will put in the regulation on what type of research can be done in that kind of like human organic sphere of research, right? And a lot of that is then reviewed and peer-reviewed by the NIH, or National Institutes of Health. That's kind of like the actual academia arm of things. And the OHRP has previously ruled on a lot of things that have gone into our current understanding of bioprinting, right? So in order to make bioink, you need the cells that go into the bioink and are suspended in the hydrogel, right? So a lot of these structures, the best way to do that, or the chosen way to do that, is not necessarily with a pure amount of a certain cells, for example, the cells that go into the stomach lining, but actually by doing using stem cells. And stem cell research has been heavily regulated. So some of the regulations that affect stem cell research will also then affect bioprinting and the production of bioink. But if that's being regulated in some way, then how are we still making progress? And that's where ARPA comes in, or ARPA-H specifically. And they are, and I quote, the high-risk, high-reward funder for medical research. So there's this greater understanding that bioprinting is a very novel technology, but it might not work, and it might not work in the way that we want it to. So with those regulating bodies and also the court of public opinion, sometimes this limits the ability to research and the use case and the ability to use technologies like bioprinting, right? So one of the things I've mentioned a lot about is stem cells, which the big ethical concern for stem cells is the use of fetal stem cells, Well, we've kind of gotten past the point where we have to use fetal stem cells in this kind of medical research. Instead, we can use, more lab-grown adult stem cells, which we know exist and know work perfectly well. But also, we have the ability to essentially create stem cells now from specialized cells. So we can take a fibroblast, which is a part of the dermis system, right? It's a part underneath of dermal cells, and that are good for elasticity and a couple of other things, and have a very definite shape, and turn them into iPSCs, which is essentially a sort of a stem cell that can become anything else, and it's kind of a reversion of these specialized cells into an iPSC, and those can be used in the same capacity that fetal stem cells or any other kind of stem cells can be used, even though that they were created from a more matured, more specialized cell, and it can be cultured from there and be used in the bioinks. So, that kind of checks off the list of, well, we can't use bioinks because they have stem cells in them and stem cells are bad, okay? But also, there's been some misunderstandings about what this kind of technology is used for, right? So again, I talk about pop culture science, and I talked about the meat berry, right? So a lot of people's introduction to the concept of bioprinting or any kind of lab-developed tissue is, okay, but can we eat it? Can I 3D print a burger? And a lot of people don't necessarily want to do that. And the answer is no, we're not really doing that, for the most part at least. Like, there's a little bit of look into it, but really it's just so amazingly cost prohibitive to try to grow all of these tissue cultures for the express purpose of just eating it. It's not really what we're using it for, but that's what people think we're using it for, and so that's what they're getting angry about. Other ethical concerns is that for research purposes, a lot of people are often okay with it, but as soon as you talk about putting something back into a person, that's a little bit of a taboo area. And some of the studies and looks at the ethical concerns as done by Penn State brought up a very interesting thing that I kind of didn't think about, and that's the use of bioprinting for the purpose of body modifications, right? So in the earlier picture, I showed a kind of combination organic prosthesis that was an ear, right? And so that is body modification. And it was put on a woman who had a congenital defect. Her right ear did not develop correctly. However, there's this idea that, okay, well, what if I just want bigger ears? Can I just, or I want detached ears instead of attached ears? Can I just, pay the money, get them printed, and then change my ears? And so that's one of the ethical concerns, and I don't think we're to the point of the technology yet that it's going to be used, for purely cosmetic sorts of things. But then again, there are a lot of things that are blurred between the concept of legitimate healthcare and cosmetics. If that one person's ear technically worked because the inner ear was fully developed and the only thing that wasn't was her outer ear, well, is 3D printing that ear a cosmetic surgery or not? And is using the technology for cosmetics considered ethical? So that's the question. But again, it's very expensive right now. The technology is not nearly refined enough for mass implementation. So these are really future questions that we're starting to ask now. All right, conclusions. So far we've covered what bioprinting is, we've covered the technology behind the bioprinters and also the bioink, some of the processes and techniques that go into that. We've covered the use cases, the 4 main use cases of tissue engineering, organ creation, drug testing for lab environments, and disease modeling, right? And then we've covered, how we're using the technology now, what's happening in the near future, and what might stop us from fully implementing the technology as it is. So the big question is Dad going to get his bioprinted organ? Is he going to wait another 5 years on the donation list? And the answer is sadly, yeah, he's going to have to wait. The technology is just not there yet. As we are making functional organs right now, a lot of them are like fetal size. So you can get a pumping fetal sized heart from some of the things that I've looked at, but not a fully sized adult one. So we are long off that technology, even if it actually ends up existing. So closing argument is, or closing question rather, knowing that bioprinting is a high risk, high reward sort of a technology, is it worth the investment? Should we continue pursuing this? And even if we can't get the most impressive results out of it, such as fully 3D printing complete organs, is what we can do enough? We can take and make parts of organs. We can take and make a swath of cardiovascular tissue, cardio tissue, vascular tissue, liver, kidney, brain, etc. And we can transplant in healthy printed amounts of tissue to replace damaged or unhealthy amounts of tissue. And that's already a lot. And the lab uses for it are amazing, to be frank. So if we never get to do more than that, is the juice worth the squeeze? And should we keep on looking at this technology? I've been Jamie Jacobson. Thank you very much for watching this presentation. Questions at the end.